this lecture, we're going to be talking about sedimentary rocks. So in this lecture, we're going to be talking about how sedimentary rocks are formed. Sediments produced by weathering at the Earth's surface can transform into sedimentary rocks. Past environments and sea level changes can be interpreted through sedimentary rocks by looking at their different composition, textures, and layering. Sedimentary accumulations occur in different parts of the world, and sedimentary rocks can be identified and classified. So last lecture, we talked about erosion and weathering, and that plays a really important part into how sedimentary rocks are formed. So sedimentary rocks are created through the cementation and compaction of sediments. There's three major classes of sedimentary rocks based on where they originated: clastic, organic, and crystalline. And in the crystalline category, we have two other little categories there. It's biochemical and chemical. And we're going to be talking about all three. Clastic sedimentary rocks. Those consist of loose clasts that have been stuck together to form a solid mass. These clasts, or grains, can consist of individual minerals or of chunks of rock. And sedimentary rocks can be formed through these different processes: weathering, erosion, transportation, deposition, and lithification. So last lecture we talked about weathering. Again, this is an example of physical weathering, like where you have a tree rooting, that breaks apart these large rocks, or you can have it on a smaller scale, how weathering can break apart grains. And we also have erosion, and erosion is the transportation part of that. So it's a combination of processes that separate the rock into the different units and their substrate. And then erosion involves things like abrasion, falling, plucking, scouring, dissolution, or even just straight up moving sediment by air, water, or ice. An example of this is out at Anacapa Island, at the Channel Islands, where the waves and the ocean has eroded away these rocks, and it creates these interesting shapes that we have today. So some of these are created by wave action, and some are also created by wind. And then we also have transportation. This can be gravity, wind, water, or ice that can carry sediment. Sediment transport depends on the viscosity and the velocity. So we talked about viscosity when it came to igneous rocks. So how viscous something is depends on how far it can be transported, as well as velocity. So something with higher velocity can be transported further. So here's an aerial photo of sediments that are being transported by currents. And so things like strong wind can move sand and dust. But if you only just have a little breeze, it can only carry the finest sediment, only a small distance. The next piece of this is deposition. It's the process by which sediment settles out of the transporting medium and it gets deposited. So when sediment settles out of wind or moving water, that occurs when the fluids slow down because the velocity decreases and the fluid no longer has the ability to carry it. So an example of this is the Mississippi River Delta, where you can see how sediment is carried over here. You can see how turbulent it looks here. And then there's a buildup of sediment down here. This would be like a depositional area where you have the current is no longer able to move sediment, and therefore it falls out of solution and then is deposited. And the last piece of this is lithification. That's the transformation of where loose clasts move into a solid rock form. And that's done in two stages. First is compaction, and that's when we have the weight of an overburden that squeezes air or water out between the grains so that the grains fit together. They're compacted together. And next is cementation, and that's where minerals precipitate from groundwater and fill those remaining spaces. And they actually bind together and are cemented together. So when you have those little spaces between the grains, those are filled and then they become cemented. So let's look at an exercise of how we can use some candy to demonstrate how sedimentary rocks are formed.
Okay, let's use some candies to demonstrate sedimentary rocks. First, let's pick a few different colors of candies here. We have some blue, green, and pink. So first we're going to weather these rocks, and I'm going to use some physical weathering. And I'm going to break some of these pieces, or cut some of these pieces in half here. And I'm going to weather these rocks. Actually, I'm going to weather these grains. Think about these as individual grains or even minerals. Okay, so now that we've done some physical weathering, let's do a little bit of erosion. So I'm going to put a little piece of candy in my hand, and I'm going to roll it around in the palm of my hand here. And now you can see that it's pretty well rounded here. Or maybe I'll take one of these other pieces and maybe not roll it as much. And this has a bit more of an angular shape to it. Maybe I'll take one of these bigger guys here and roll him into a ball. Okay. Perfect. Okay, so now we have our first weathering, second erosion, third deposition. Push them all together to a nice little pile. And now next is compaction and cementation. So I'm going to press these together, use a little bit of force here, push them together for my compaction, and now they're cemented together. They're stuck to each other. They aren't coming apart. And now lastly, what we can do is fold it into a pancake. Squish it together. And now you can see that we have all of these individual grains or minerals mushed together into one nice sedimentary rock.
Okay, so there's a few different ways that we can classify clastic sedimentary rocks. First is clast size, clast composition, angularity and sphericity, sorting, and the character of cement. So let's talk about what those mean. First is clast size, and this refers to the diameter of fragments or grains making up a rock. So if you look at the chart over here, you can see that the grain size can be defined by these literally measurements of grains. So if you have a clast size of a pebble, that could be 4 to 64 millimeters. Things like a coarse sand would be 0.5 to 2 millimeters. And somewhere around here between a coarse sand and a medium sand, maybe fine sand is something that you'd be able to visibly see if you had those clasts in the palm of your hand. Much smaller than that, like fine sand and silt, 0.004 to 0.06 millimeters. Those are really hard to see. So this is a shorthand of how we would describe the clast size. No one really knows that a pebble is 4 to 64 millimeters, but this is a way that we say, oh, it's about pebble size, or it's about a medium sand or a fine sand. Okay, next is a clast composition, and this refers to the makeup of clasts within the sedimentary rock. So clasts can be composed of rock fragments or individual mineral grains. Okay, next is the angularity or sphericity. So angularity indicates the degree to which clasts have smooth surfaces or angular corners or edges. And the sphericity refers to how much it resembles an actual sphere. So we use words like angular to rounded, and in between we have subangular and subrounded. So if you were to imagine a river that pushes rock down the river and it gets tossed around a lot, at the if it's tossed around for a really long time, that becomes rounded because the rock moves within the water for a longer period of time. It gets pushed around, and so those edges get cut off. And so you come, at the end of a river mouth or something, you'd see really rounded clasts versus angular, which means that they haven't gone through a lot of erosion or deposition. Okay, next is sorting. Sorting indicates the portion of clasts in rock that has relatively the same size to each other. So a well-sorted sediment consists entirely of clasts that are the same size, whereas poorly sorted means that there's a big mixture of them. So if we were to look at this picture here, a very poorly sorted clast would have really large clasts with very small. And in contrast, if we look at a very well-sorted, all of the clasts are about the same size. And then we have different levels of severity in between poorly sorted, moderately sorted, well-sorted. And this is a way that we'd be able to describe how well the clasts are sized relative to each other. And then these different things, the different sorting can tell us about how they're deposited and at what time they're deposited. Okay, next is the character of cement. So not all classic sedimentary rocks contain the same kind of cement. In some, the cement consists of quartz, whereas others are predominantly calcite, and this has to do with where the clasts are deposited and what the environment is. Because we have these grains that are smushed next to each other, and we have this pore space in between. So if you think about having a jar of marbles, the space in between the marbles is what we call pore space, and that pore space can be filled with fluid. But when we talk about how these pore spaces get crushed and filled to create a sedimentary rock, this is where we get that cementing going on. This is where we have calcite that fills those pore spaces, or we have quartz that fills those pore spaces. And that's what we call the cement. That's what binds the grains together. So here's some examples of that. Here's a picture of breccia. You can see that this has a very poorly sorted and very angular looking clasts. This clast is a very different size than the clast next to it. Next, we have conglomerate. So these clasts are a little bit similar in size. Some are angular, some are a little bit more rounded, but you can really see the difference here between the clasts and the cement. So the clasts are this more yellowish, sandy color, and the cement is the grayish color that's behind it. Okay, down here is a sandstone, and you can't really see individual grains. So this is fairly well sorted, I would say. There are a few other outstanding grains here that are distinctly larger than the surrounding mass. And in here, we can't distinguish necessarily the grain to the cement like we can in a conglomerate. Next is a siltstone, and this is very fine grained. And again, we don't really see any distinct shapes of different grains. We also can't really see individual clasts. So these clasts are much smaller. If I had the sample in front of me, I wouldn't be able to see individual grains or clasts because they're so small. And next here is a shale. So the difference between a siltstone and a shale is predominantly, well, first the color. You can see that for yourself, that the color is quite different. Shale is much darker, and that has to do with how they're formed and what type of minerals contribute to the formation of siltstone versus shale. Okay, so let's talk about organic sedimentary rocks. In some environments, organic debris settles along with other sediment, and it's eventually buried. So here's a picture of coal, and coal is black combustible rock that contains between 40 to 90% carbon, and the remainder is oxygen, nitrogen, hydrogen, sulfur, and silica. And coal is formed when plant remains, like swamps or trees or anything like that, that have been buried deeply enough and long enough that the material becomes compacted, and it can lose a large amount of its volatiles. So like it has that those combustible qualities, those volatiles like gases. In contrast, down below, we have the oil shale. So in the previous slide, I showed just a normal shale. Well, what's the difference between a shale and an oil shale? And so a shale contains clay, but 15 to 40% organic material is called kerogen. So the kerogen in oil shale comes from the fats and proteins that made up living part of plankton or algae or other little critters. And when these organisms mix with the clay minerals and mud, they get buried, lithified, and then the organic material then forms into kerogen or oil. Okay, so let's talk about biochemical sedimentary rocks. When organisms die, the solid material in their shell survives, and that material then is lithified, and it comprises what we call a biochemical sedimentary rock. So in the top right, here's a picture of a biochemical limestone. You can see these little shells right here. And these are organisms make solid shells of calcium carbonate that then crystallize as calcite or aragonite. And limestone is often referred to as a carbonate rock. So when we talk about depositional systems, we talk about carbonates. And so a limestone is typically called a carbonate rock. And down below, here's an example of a biochemical chert. And this is made from crystalline quartz. And these are where shells have dissolved, forming a silica-rich gel, which is then solidified. So these were once shells that have been crushed up and dissolved and then solidified over time. Okay, next we have chemical sedimentary rocks. And this is where we have rocks that are formed primarily by the precipitation of minerals from water solutions, like when we have ocean water or brine. And they typically have crystalline texture. They're partly formed during the original precipitation and partly formed later when new crystals grow at the expense of old ones. And we have recrystallization. An example of this is called evaporites. And this is the product of saltwater evaporation. So if I move my face, and in this diagram over here, so say we have this system where we have shallow water evaporates that are being deposited here, and we have an ocean here, which we have salt water. And so as the sea level falls and we have evaporation, we have these evaporites that get deposited into the sediments. And then later on, if we have sea level rise and we have periodic overflow or seepage into the nearby sediments here, then we have the recrystallization of these evaporites. Okay, so another example of chemical sedimentary rocks is travertine. And you may have seen travertine. It's a little bit popular to make floors out of or countertops. This is chemical limestone, and it's composed of crystalline carbonate formed by chemical precipitation from groundwater that has seeped out of the ground surface in springs or the walls of caves. Next is dolostone. That's the example down here in the bottom right. This contains mineral dolomite, or calcium and magnesium. And the magnesium comes from groundwater, and there is a reaction between the groundwater and the calcite. So dolostone is typically found beneath lagoon systems. And last, an example of chemical sedimentary rocks is chemically precipitated chert. And this is formed when quartz gradually replaced those calcite crystals. And chert can come in many different colors depending on the impurities that it contains. Here's an example of precipitated chert, petrified wood. petrified wood is actually considered a sedimentary rock. And it forms when plant material is buried by sediment and protected from decay. So typically, if you have a tree that's fallen over, it would rot over time. But if it gets buried, then it's protected from the oxygen and other organisms that could cause the wood to decay. So groundwater dissolves the solids that flow through the sediment and replaces those plant materials with silica or calcite or pyrite or other inorganic material, even like opal. So sometimes maybe you'd see petrified wood that's quite shiny. That would be an example of where pyrite or opal would be precipitated into that material. And the result is a fossil, basically, of the original woody material. And if you've seen petrified wood, it looks like a log of wood. It's quite interesting to see. If we were in the classroom setting, I would show you an example, and you'd go, "Ooh, look at that petrified wood." Okay, so hope you have your sheets handy, because now we're going to watch a video on sedimentary rocks, and make sure to fill out that sheet along the way.
In this video, we're going to be talking about sedimentary rocks. Please make sure to have your rocks flowchart ready, as we're going to be filling in another portion of it today. Let's get started. Of course, as I mentioned, we're talking about sedimentary rocks, the second variety of rocks in our rocks chapter. Please recall that rocks are classified according to the way in which they formed. So, for example, igneous rocks form from the cooling and solidification of magma or lava. Now, sedimentary rocks form in an entirely different way, which I'd like to describe now. The general way in which most sedimentary rocks form is from the compaction and cementation of sediments. Now, there are some words there that we need to talk about. First off, compaction means what you might think: compacting, squeezing together. Cementation means gluing or cementing, sticking together sediments. But that brings up yet another question. So if these rocks are formed from the compaction and cementation, the squeezing and gluing of sediments, well, what exactly are sediments then? Well, sediments are the fragments, the little bits of rock that have been broken down as a result of a process known as weathering. Weathering includes wind and ice, running water, etc. So imagine you have a big boulder sitting in your backyard. Well, if you were to somehow magically leave the earth and come back 10,000 years from now, that boulder might look very different. As a result of years of wind blowing against it and ice cracking it apart and water flowing over its surface, it will have broken down into smaller and smaller pieces. That's what sediments are, the small fragments that result from the weathering of rock. Sediments, interestingly, are classified according to their size. So we actually have 6 categories of sediment sizes, the smallest being clay, then silt, then sand, then pebbles, cobbles, and boulders being the largest. So you've heard the term sand before. Now you know that it actually just refers to a size of particle, not a specific material. If you want to know the specific sizes that make sediments fall into any of these categories, you can find that information on page 6 of your Earth Science reference tables. You can ignore the graph portion of this chart, as we haven't learned about it yet. However, I'd like you to pay attention to the names of the sediment sizes on the right-hand side that I've highlighted in green. They will tell you how big each sediment is. So let's use sand as an example. For a sediment to be considered sand-sized, it would have to be between 0.006 centimeters and 0.2 centimeters. Anything bigger would be a different type, as would anything smaller. Another example, boulders are considered any sediment that are larger than 25.6 centimeters in size. Now, let's talk about the first type of sedimentary rock, because there really are 3 types. The first type of sedimentary rock is called a clastic sedimentary rock. Now, a clast is actually just a fancy word for a sediment. So these are actually the types that we have already been discussing. These clastic sedimentary rocks form from compacted sediments, and these are generally classified according to their size. Let's take a look at the Sedimentary Rocks reference table. Now, the clastic rocks are the ones that are on the top half. They are also referred to as the inorganic, because they don't involve any living materials, and land-derived, meaning they come from the land. They come from the rock that makes up the land. Now, if you'll notice under grain size, you can see the different size sediments that make up each of the rocks. Composition tells you what minerals you would expect to see. Comments are just important information. And then, of course, you have the names of the rocks and something called the map symbol, which we'll be using more later in the year. So let's take a look at some of these clastic sedimentary rocks, beginning with the first one, conglomerate. Conglomerate is composed of all different size sediments or clasts compacted and cemented together. So you'll have big cobbles, pebbles, maybe even boulders, compacted with small sand, silt, and clay. Notice that the sediments in a conglomerate are rounded out, likely due to flowing water that ran over them sometime in the past. Very similar to a conglomerate is a breccia. Breccia, too, is made of all different sized sediments compacted and cemented together. The difference being the sediments in a breccia are not rounded. They are more angular, pointy, or jagged. Then we get to the sandstone. As you can imagine, sandstone is made of compacted sand grains. Siltstone, made of compacted silt. And shale, made of compacted clay particles. So those are your clastic sedimentary rocks. Compacted and cemented sediments. Now, back to our chart. Let's look at another type. Let's actually look at the other two types. We have organic and crystalline sedimentary rocks. For the crystalline, we have things called evaporites and precipitates. And then for the organic, we have what we call biological matter rocks or bioclastic rocks. Let's talk about these, as they are a little bit more complex. First off, the crystalline rocks, seen here on the reference table. So these are under a column that says chemically or organically formed sedimentary rocks. So these are not necessarily from compacted sediments. In fact, the crystalline ones form in an entirely different way. So crystalline sedimentary rocks are known as evaporites or precipitates. And what that means is that they form as a result of some sort of chemical process. Let's take a look at some examples. This is probably the best example. This is rock salt. Now, rock salt forms from seawater, which of course has salt, or halite, dissolved in it. And when that water evaporates, the salt stays behind in the form of crystals. Those crystals are the rock salt. This is why it's called an evaporite. This is also why it's called crystalline, because it's crystals of salt that were left behind after evaporation occurred. We also get other rocks like rock gypsum and dolostone that form in similar ways. Just to mention the precipitate, this is a similar process, however, as the name implies, it does not involve evaporation like rock salt does. A precipitate forms when a water sample is completely filled with a dissolved mineral, so much so that the mineral falls out of being dissolved and crystallizes in the bottom of a body of water. To summarize, the crystalline rocks all involve some sort of chemical process, whether it's evaporation or precipitation. The result would be rock salt, rock gypsum, or dolostone. But what about these biological rocks, the bioclastic rocks? Now these form from compacted organic material or organic matter. We already know some examples of these, which include coal, which forms from compacted plant remains, and then this, which is a variety of limestone called a coquina. And you'll notice this is made of compacted shells. Shells, of course, are made by sea creatures. This is organic material, and so being classified as a bioclastic rock because it's organic matter that's been compacted together. One more key note about sedimentary rocks is that they are the only type of rock that may contain fossils or evidence of past life. So if you see a rock with a fossil in it, you know automatically it must be a sedimentary rock. The reason being, the processes that involve the formation of igneous and metamorphic rocks involve a lot of heat and or pressure. And so these processes would destroy any fossils that existed. Therefore, the only type of rocks that really commonly contain fossils are sedimentary rocks. We'll learn all about this in school. Thanks for listening.
Let's talk about sedimentary structures. This is the layering of sedimentary rocks, or surface features on layers that are formed during deposition and the arrangements of grains within the layers. Some examples of this would be bedding, stratification, ripple marks, dunes and cross-bedding, turbidity currents and graded beds, and bed surface markings. So the note here that I have at the bottom of this slide is that there's a whole discipline, a subset discipline of geology called geomorphology. And it's the scientific study of the origin and evolution of topographic and bathymetric features created by the physical, chemical, or biological processes operating at the Earth's surface. And so geomorphologists look at these different sedimentary structures, and it's kind of like being an investigator or something. You look at these structures and you try to figure out how did it get there. And so it's an integral discipline of geography, geology, engineering, climatology. It's a really interesting field, and I could talk about geomorphology for a long time. And I think that studying depositional environments is very interesting because it's like stepping back in time, trying to figure out what happened in the subsurface during that time. So let's talk about bedding and stratification. So the words in bold on this slide are some words that I'm going to be using throughout the semester. So these are some definitions of those in the context of sedimentary rocks. So a single layer of sediment or sedimentary rock with a recognizable top and bottom is called a bed. The boundary between those two beds is called a bedding plane. And several beds together constitute a strata. The overall arrangement of sediment into a sequence of beds is called bedding. Sequence of strata that is distinctive enough to be traced as a unit across a large region is called a stratigraphic formation. So bedding and stratification occurs when there is a change in depositional environment. So if we go from being underwater to being on top of the water, and then you'd see a very distinctive change in the sediments, and that would be along that change is where we have a bedding plane. And between those two different stratas is where we'd have a change in formation. And so these are just some words that I might be using throughout the semester. So try and get familiar with the differences between these. Okay, so like I said, over time, there's different depositional systems that bring in different types of sediments, and they're brought in different processes. So for example, there are sediments brought in by a stream. So over time, we have this silt that's being deposited from a normal river, and then say there's a flooding event, and so you get a lot of different sediment. During a flooding event, you'd see much larger sediment as opposed to small layers of silt that would be deposited in just a river. And so over time, you have this, say this is an area that is known to be have water flow, but then also has flooding events. So you'd see a layer of silt or clays, and then a layer of gravel, and then another layer of silt and clays, and another layer of gravel. And so here's an example of that, where you have these distinctive beds. So again, here are all the individual beds. This all looks fairly similar in the composition. So this would be one formation. And between, this looks a little bit different. These rocks up here look different than these rocks. So along here would be a bedding plane. Okay, so let's talk about other sedimentary structures. Ripple marks are elongated ridges that form on a bed surface at right angles to the direction of current flow. So here's an example of some ripple marks. And dunes look like ripples, but they're only larger. And typically ripple marks are made from water processes, whereas dunes are made from air. And then here's an example of crossbeds. And crossbeds are internal laminations that are inclined at an angle to the main sedimentary layer. So you can see how these are crossbeds that are cross-cutting the main bed structure. Okay, next, turbidity currents and graded beds. So sediments deposited on a submarine slope tend to be unstable. So a big event like an earthquake or a storm might disturb them, and that causes them to slip downslope. This will make a turbulent cloud, which flows like an underwater avalanche. And the further downslope it is from the current, like when we have more velocity, the coarser sediment settles out first. And progressively further away from the source is where we have the finer grains. And so an example of this is where we have coarser grains here at the bottom and finer grains at the top. So again, these are some words that we would describe these clasts here. So we have really large clasts. They're quite angular. Some are a little bit more rounded. And then as we look further up into this sedimentary rock, we see that you can't really define individual grains. So this is a fine grained, this is coarse grain. And to describe graded bedding, we say this is fining upward. So you can impress all of your friends by saying the word fining upward when you look at graded beds. Okay, so here's some other bed surface markings. We have mud cracks, and this is when we have a layer of mud or clays that dry up, and then it creates these really large cracks. Here's an example of scour marks, and this is where fluid flow erodes through troughs, and this is typically done in parallel to the flow. And of course, we have shells, shell imprints on a bedding surface, and leaves the imprint. Okay, so I have a whole lecture devoted just to depositional environments. So when we talk about depositional environments, these are conditions in which sediment was deposited. So we can divide these up into two. First is terrestrial, which is like on land, non-marine. And then we have coastal or marine sediment. So some examples of terrestrial sedimentary environments are glaciers, mountain streams, alluvial fans, deserts, rivers, and lakes. And then in coastal and marine sedimentary environments, these are basically from high tide line all the way into offshore. We have things like marine deltas, coastal beaches, shallow marine clastics, and carbonates. Do you remember the difference between the two? And then we also have deep marine. So we're going to be talking a lot about depositional environments in the next lecture. Okay, we're almost done. Okay, last is sedimentary basins. And these are areas around the world where there's large accumulations of sedimentary rocks. So there's a few different things here. We have categories of basins in the context of plate tectonics, because plate tectonics is the foundation of everything. So where do we see large sedimentary basins based on plate tectonics? We're going to talk about that. We have transgression and regression and diagenesis. Okay, so where do we see sedimentary basins and how are they associated to plate tectonics? So in rift basins, these form in continental rifts. So as the rift grows, we have large blocks of crust that drops down and fills the basement with terrestrial sediment. We also see this in passive margins. This forms in the edges of the continents where there are not plate boundaries, but they're remnants of rifts where evolution successful led to the formation of a mid-ocean ridge. And these typically form because we have subsidence of the lithosphere, and that continues long after the rift ceases and fills with sediment. And then we have intracontinental basins, and these develop in the interior of continents. So these initiate subsidence and then continue to subside hundreds, up to thousands of years after they initially formed. So these are some examples of where we see large sedimentary basins in relationship to plate tectonics. Okay, so some other keywords here: transgression and regression. Transgression is where we have general sea level rise. Regression is where we have sea level fall. And so over the course of geologic time, we see a lot of sea level rise and sea level fall. Currently, in our human history right now, we're seeing a sea level rise, which would be a transgression. And so during these different sea level phases, we see how that affects different sediment deposition. So when sea level rises, we have typically more deposition, and we see that further away we have limestone, mudstone, and then closer to the coast we have sandstone. And as the sea level rises, it pushes the sediments into a diagonal direction that is roughly parallel to the coastline. And in a regression state where sea level falls, the water pulls some of these sediments back. And so we can see now that if we have sandstone and mudstone and limestone, we have these three different rocks, we can see how over time, as the sea level falls and regresses, that these sediments are being pulled backwards in a more parallel, or I should say perpendicular to the slope. So there's these little clues that we can use by looking at sediments and rocks to tell us about relative sea level trends, if it's rising or falling. Okay, lastly is diagenesis. And this is a physical, chemical, and biological process that transforms sediments into a sedimentary rock that alter the characteristics of the sedimentary rock after the rock is formed. So an example of this is how quartz can undergo diagenesis. And we see that over different temperatures and different amounts of silicas, this rock actually can transform into something else. So an example of this is the Monterey Formation, which is very prevalent here in California. And we're going to be talking about that when we talk about petroleum systems, and how the Monterey Formation basically goes through diagenesis in relationship to how much silica it is. So as it gets hotter with increased silica, the rock turns from opal A to opal CT to quartz. So you don't really have to know too much about this, other than diagenesis is a process that occurs that combines both physical, chemical, and biological processes. Okay, so what did we learn? The three major classes of sedimentary rocks are clastic, organic, and crystalline. We looked at examples of all three. There are sedimentary structures that include bedding, cross-bedding, ripple marks, dunes, and mud cracks, and they give us clues to the past of how these rocks were deposited. Sedimentary rocks have different composition, like how limestone has calcite, chert contains silica, shale has clay, and so on and so forth. And different depositional environments give us clues to what the Earth was like in that geologic time. We can use the past to tell us about the present and vice versa. So we look at environments that we see today, and we can try and use our detective skills to figure out what the Earth was like. That's it for this lecture. See you next time.